A partially crimped ground connection on a residential service resulted in a loose connection after being bumped. The loose connection caused an overvoltage surge, damaging electronic devices in the home. The original lineman responsible for the incomplete crimping did not return to finish the job or retrieve their battery-powered crimping tool. The proper connector was used but not fully crimped, allowing the connection to fail. This incident highlights the importance of attention to detail and thorough inspections in electrical work to prevent potential hazards. Ensure that all electrical connections are properly and completely crimped using the correct tools and techniques. After completing electrical work, thoroughly inspect all connections to verify their integrity and tightness. Always prioritize safety by turning off power before handling electrical components. Electricians should be held responsible for the quality of their work and should return to complete unfinished tasks promptly. Communicate any issues or incomplete work to the customer and take steps to resolve them quickly. Even seemingly small details, such as fully crimping a connection, can have significant consequences. When performing electrical work, especially on a service entrance, it's crucial to adhere to best practices to ensure safety and prevent future issues. Here's a detailed look at the steps and considerations for a 200 amp residential service installation. Firstly, planning and preparation is essential. Before starting any electrical work, it's important to plan the entire installation. This includes determining the location of the service panel, meter, and grounding system. Obtain all necessary permits and ensure compliance with local electrical codes and the National Electrical Code (NEC). Verify that all materials and equipment are on hand and in good working condition. This includes the correct size and type of conductors, connectors, and tools. Secondly, safety precautions are paramount. Always turn off the power to any existing electrical circuits before starting work. Use appropriate personal protective equipment (PPE) such as gloves, safety glasses, and insulated tools. Follow lockout-tagout procedures to prevent accidental energization of circuits while working. Thirdly, grounding system installation is critical. Install a grounding electrode system that meets NEC requirements. This typically involves driving ground rods or using a concrete-encased electrode, also known as a UFA ground. Connect the grounding electrode conductor (GEC) to the grounding electrode in the service panel. Ensure all connections are tight and properly protected from corrosion. Fourthly, service entrance cable installation should be done carefully. Run the service entrance cable from the point of attachment at the utility drop to the meter base and then to the service panel. Support the cable properly along its route using appropriate clamps and supports. Ensure the cable is protected from physical damage where it passes through walls or other structures. Fifthly, meter base installation is next. Install the meter base according to the manufacturer's instructions and local utility requirements. Ensure the meter base is securely mounted and properly grounded. Make sure the meter base is accessible for meter reading and maintenance. Sixthly, service panel installation is vital. Mount the service panel securely in a location that is easily accessible and protected from moisture. Connect the service entrance conductors to the main breaker in the service panel. Ensure all connections are tight and properly torqued according to manufacturer's specifications. Seventhly, bonding is very important. Bond the neutral conductor to the service panel enclosure. Connect all metallic components, such as conduit and enclosures, to the grounding system. Use appropriate bonding jumpers to ensure continuity of the grounding path. Eighthly, conductor termination needs to be performed. Carefully strip the insulation from the conductors without nicking or damaging the wire. Use the correct type and size of connectors for the conductors being terminated. Tighten all connections to the manufacturer's specified torque using a calibrated torque wrench. Ninthly, circuit breaker installation is necessary. Install circuit breakers of the correct size and type for each branch circuit. Label each circuit breaker clearly to indicate the area or equipment it serves. Ensure all circuit breakers are properly seated and securely connected to the bus bar. Tenthly, inspection and testing should be done. After completing the installation, thoroughly inspect all connections and components to ensure they are properly installed and tightened. Use a multimeter to verify proper voltage and continuity. Test the operation of all circuit breakers and other protective devices. 11thly, documentation is important. Keep a detailed record of the installation, including wiring diagrams, circuit breaker schedules, and inspection reports. Provide the homeowner with a copy of the documentation for their records. Maintain a copy of the documentation for future reference. Crimping tools are essential for making secure and reliable electrical connections. There are several types of crimping tools available, each designed for specific applications and connector types. Here's a rundown of common crimping tools and their proper usage. Firstly, manual crimpers are commonly used for small gauge wires and terminals. These tools rely on manual force to compress the connector around the wire. They typically have color-coded dies or markings to match the appropriate connector size. To use a manual crimper, strip the wire to the correct length. Insert the wire into the connector. Place the connector into the appropriate die on the crimping tool. Squeeze the handles of the crimping tool until the connector is fully compressed. Secondly, ratchet crimpers provide a more consistent and reliable crimp compared to manual crimpers. These tools have a ratchet mechanism that ensures the connector is fully compressed before the tool can be released. They are available for a variety of connector types and wire sizes. To use a ratchet crimper, strip the wire to the correct length. Insert the wire into the connector. Place the connector into the appropriate die on the crimping tool. Squeeze the handles of the crimping tool until the ratchet mechanism releases, indicating a full crimp. Thirdly, hydraulic crimpers are used for large gauge wires and heavy-duty connectors. These tools use hydraulic pressure to compress the connector around the wire, providing a very strong and reliable connection. They are commonly used in industrial and commercial applications. To use a hydraulic crimper, strip the wire to the correct length. Insert the wire into the connector. Place the connector into the appropriate die on the crimping tool. Use the hydraulic pump to apply pressure until the connector is fully compressed. Fourthly, battery-powered crimpers offer convenience and portability for field installations. These tools are powered by rechargeable batteries and provide consistent crimping force. They are available for a variety of connector types and wire sizes. To use a battery-powered crimper, strip the wire to the correct length. Insert the wire into the connector. Place the connector into the appropriate die on the crimping tool. Activate the tool to compress the connector around the wire. Fifthly, specialized crimpers are designed for specific types of connectors, such as coaxial connectors, RJ45 connectors, and fiber optic connectors. These tools have specialized dies and features to ensure proper crimping of these connectors. To use a specialized crimper, follow the manufacturer's instructions for the specific connector type. Ensure that the connector is properly aligned in the tool before crimping. Apply the appropriate amount of force to compress the connector around the wire or cable. Always follow the manufacturer's instructions for the specific crimping tool and connector being used. Use the correct die size and settings for the wire gauge and connector type. Inspect the crimped connection to ensure it is secure and meets the required specifications. Regularly maintain and calibrate crimping tools to ensure accurate and reliable crimping performance. Replace worn or damaged dies and components as needed. Store crimping tools in a clean and dry place to prevent corrosion and damage. Proper crimping techniques are crucial for ensuring safe and reliable electrical connections. Firstly, wire preparation is very important. Strip the insulation from the wire to the correct length, exposing the conductor. Use a wire stripper tool to avoid nicking or damaging the wire strands. Twist the exposed wire strands together tightly to create a solid conductor. Secondly, connector selection is also something to consider. Choose the correct type and size of connector for the wire gauge and application. Ensure the connector is compatible with the crimping tool being used. Use connectors that are listed and labeled by a recognized testing laboratory, such as UL or ETL. Thirdly, crimping process is key. Place the connector onto the wire, ensuring the conductor is fully inserted into the connector barrel. Position the connector in the appropriate die of the crimping tool. Apply firm, even pressure to the crimping tool until the connector is fully compressed. Follow the manufacturer's instructions for the specific crimping tool and connector being used. Fourthly, inspection is needed to verify that it is good to go. Inspect the crimped connection to ensure it is secure and meets the required specifications. Check for proper deformation of the connector barrel around the wire. Verify that the wire is fully inserted into the connector and that no strands are exposed. Fifthly, testing should be done after inspection. Perform a pull test to ensure the crimped connection can withstand the expected mechanical stresses. Use a multimeter to verify electrical continuity through the crimped connection. Document the results of the inspection and testing for future reference. Overvoltage can occur in electrical systems due to a variety of factors. These surges can damage sensitive electronic equipment and pose a safety hazard. Understanding the causes and implementing protective measures is essential. Firstly, lightning strikes can create significant overvoltage. Direct lightning strikes to power lines or nearby structures can induce high voltage surges in electrical systems. These surges can travel through the wiring and damage connected equipment. Lightning arresters and surge protective devices, SPDs, can help to divert these surges to ground, protecting equipment from damage. Secondly, utility switching can be a source of overvoltage. Utility companies may perform switching operations on their distribution systems to reroute power or perform maintenance. These switching operations can create voltage transients that propagate through the electrical grid. SPD installed at the service entrance can help to mitigate these voltage transients. Thirdly, internal faults can cause overvoltage within a building's electrical system. Short circuits, ground faults, and other electrical faults can cause voltage spikes that damage equipment. Circuit breakers and fuses are designed to interrupt the flow of current during a fault, but they may not always respond quickly enough to prevent damage from voltage surges. Fourthly, inductive loads can contribute to overvoltage. Equipment with inductive loads, such as motors, transformers, and fluorescent lights, can generate voltage transients when they are switched on or off. These transients can be particularly problematic in systems with a large number of inductive loads. SPD installed at the equipment can help to suppress these voltage transients. Fifthly, electrostatic discharge, can also cause damage. ESD can occur when a static charge is discharged from a person or object into an electronic device. These discharges can damage sensitive electronic components. Proper grounding and bonding techniques can help to reduce the risk of ESD. Sixthly, improper wiring can also cause overvoltage. Incorrect wiring, such as reversed polarity or loose connections, can create voltage imbalances that damage equipment. Regular inspections and maintenance can help to identify and correct wiring errors. SPD are designed to protect electrical and electronic equipment from voltage surges. There are different types of SPD available, each designed for specific applications and voltage levels. Firstly, Type 1 SPD are installed at the service entrance of a building. They are designed to protect against high-energy surges caused by lightning strikes and utility switching. Type 1 SPD are typically hardwired into the electrical system. Secondly, Type 2 SPD are installed at distribution panels or subpanels. They are designed to protect against lower energy surges caused by internal faults and inductive loads. Type 2 SPD can be hardwired or plug-in devices. Thirdly, Type 3 SPD are installed at the point of use, such as at an outlet or equipment. They are designed to protect against very low energy surges caused by ESD and other localized disturbances. Type 3 SPD are typically plug-in devices. When selecting an SPD, it's important to consider the voltage rating, surge current capacity, and protection mode. The voltage rating should match the voltage of the electrical system being protected. The surge current capacity should be high enough to handle the expected surge currents. The protection mode should provide protection for all conductors, including line to neutral, line to ground, and neutral to ground. Proper grounding and bonding are essential for the effective operation of SPD. The SPD should be connected to a properly grounded electrical system. All metallic components, such as conduit and enclosures, should be bonded together to create a low-impedance ground path. Regular inspections and maintenance are important to ensure that SPD are functioning properly. SPD should be inspected periodically for signs of damage or degradation. Replace SPD that have been damaged or have reached the end of their service life. Communication is a critical aspect of any electrical project. Clear and effective communication between electricians, customers, and other stakeholders can help to prevent misunderstandings, ensure safety, and promote a positive working relationship. Firstly, pre-job communication should be done. Before starting any electrical work, it's important to communicate with the customer to understand their needs and expectations. Discuss the scope of the project, the timeline, and the potential costs. Provide the customer with a written estimate outlining the work to be performed and the materials to be used. Obtain the customer's approval before starting work. Secondly, on-site communication is important during the project. Keep the customer informed of the progress of the work. Communicate any changes to the scope of the project or the timeline. Address any questions or concerns the customer may have. Maintain a professional and respectful attitude at all times. Thirdly, safety communication is essential. Communicate safety procedures and precautions to all workers and customers. Ensure everyone understands the potential hazards and how to avoid them. Use clear and concise language when communicating safety information. Post safety signs and warnings in visible locations. Fourthly, problem-solving communication is necessary. If any problems arise during the project, communicate them to the customer and the project team. Work together to find solutions that meet the customer's needs and comply with safety regulations. Document all problems and solutions for future reference. Fifthly, post-job communication is important to finalize the project. After completing the work, walk through the project with the customer to ensure they are satisfied. Explain the operation of any new equipment or systems. Provide the customer with a written warranty for the work performed. Address any remaining questions or concerns the customer may have. Sixthly, documentation is something to consider for future reference. Keep a detailed record of all communication with the customer. Document any agreements, changes, or problems that occurred during the project. Maintain a copy of all documents for future reference. Effective communication can help to prevent disputes and ensure customer satisfaction. Respond promptly to customer inquiries and concerns. Listen carefully to the customer's needs and expectations. Be transparent and honest in all communication. Follow up with the customer after the project is completed to ensure they are satisfied with the work. The incident described highlights the importance of accountability in electrical work. When an electrician fails to complete a task properly, it can have serious consequences, including property damage and safety hazards. Electricians should be held responsible for the quality of their work and should take steps to correct any mistakes or omissions. Firstly, quality control is very important. Electricians should implement quality control procedures to ensure that all work is performed to the highest standards. This includes using the correct tools and materials, following proper installation techniques, and thoroughly inspecting all connections. The electrician should also stay up to date on the latest codes and standards. Secondly, supervision is key to accountability. Electrical contractors should provide adequate supervision to ensure that all workers are performing their jobs correctly. Supervisors should regularly inspect work in progress and provide feedback to workers. Supervisors should also be available to answer questions and provide guidance. Thirdly, training can improve the skills of the workers. Electrical contractors should provide ongoing training to ensure that all workers have the skills and knowledge necessary to perform their jobs safely and effectively. Training should cover a wide range of topics, including electrical theory, code requirements, and safety procedures. Fourthly, insurance should be considered to protect against liability. Electrical contractors should carry adequate insurance to protect themselves against liability in the event of an accident or injury. Insurance can help to cover the cost of damages, medical expenses, and legal fees. Fifthly, licensing is required in most jurisdictions. Electricians should be licensed and insured to demonstrate their competence and professionalism. Licensing requirements vary by jurisdiction, but typically include passing an exam and completing a certain amount of on-the-job training. Sixthly, ethics are important to prevent future problems. Electricians should adhere to a code of ethics that emphasizes honesty, integrity, and professionalism. This includes treating customers fairly, providing accurate information, and respecting the safety of others. Accountability can help to improve the quality of electrical work and reduce the risk of accidents and injuries. Take responsibility for your actions and learn from your mistakes. Seek feedback from customers and colleagues to identify areas for improvement. Continuously strive to improve your skills and knowledge. Here are some guidelines that will help in performing thorough inspections in electrical work, and they include: firstly, visual inspection. Conduct a visual inspection of all electrical components, including wiring, connections, and equipment. Look for signs of damage, such as frayed wires, cracked insulation, or loose connections. Check for proper labeling and identification of circuits and equipment. Secondly, testing and measurement are important. Use a multimeter to verify voltage, current, and continuity. Test the operation of all circuit breakers and other protective devices. Perform ground impedance testing to ensure the grounding system is functioning properly. Thirdly, code compliance checks are necessary. Verify that the installation complies with all applicable electrical codes and standards. Check for proper wire size, conduit fill, and overcurrent protection. Ensure that all equipment is listed and labeled by a recognized testing laboratory. Fourthly, safety checks are crucial. Inspect for potential safety hazards, such as exposed wiring, overloaded circuits, and improper grounding. Verify that all safety devices, such as ground fault circuit interrupters, GFCIs, are functioning properly. Ensure that all electrical equipment is properly guarded and protected from physical damage. Fifthly, documentation review is key. Review all documentation, including wiring diagrams, circuit breaker schedules, and inspection reports. Verify that the documentation is accurate and up to date. Ensure that the documentation is readily available for future reference. Sixthly, follow-up is a must. After completing the inspection, provide a written report outlining any findings or recommendations. Follow up with the customer to ensure that any necessary repairs or corrections are made. Maintain a record of all inspections and follow-up actions. Thorough inspections can help to identify potential problems before they cause damage or injury. Take your time and be thorough in your inspections. Use a checklist to ensure that you don't miss anything. Don't be afraid to ask questions if you're unsure about something. Overvoltage events can be caused by a variety of factors, some originating from within a home's electrical system and others from external sources. Understanding these causes is crucial for implementing effective protective measures. Firstly, internal causes may include faulty wiring. Incorrect or deteriorated wiring can lead to voltage imbalances and spikes. Loose connections, damaged insulation, or improper grounding can create pathways for overvoltage events. Secondly, appliance malfunctions may cause problems. Malfunctioning appliances, especially those with motors or transformers, can generate voltage surges when they switch on or off. These surges can propagate through the home's electrical system and affect other devices. Thirdly, overloaded circuits may cause overvoltage. Overloading a circuit by plugging in too many devices can cause the voltage to drop and then surge when the load is removed. This sudden voltage change can damage sensitive electronics. Fourthly, external causes may include lightning strikes. Lightning strikes near a home can induce high voltage surges in the electrical system, even if the strike doesn't directly hit the house. These surges can travel through power lines and damage any connected devices. Fifthly, power grid issues can create surges. Problems with the power grid, such as switching operations or equipment failures, can cause voltage fluctuations and surges that affect homes connected to the grid. Sixthly, electromagnetic interference or radio frequency interference, ME or RFI, can affect electrical circuits. Strong electromagnetic fields from nearby sources can induce voltages in wiring, leading to overvoltage events. Surge protective devices, SPDs, are essential for mitigating the risks of overvoltage events. These devices divert excess voltage to ground, protecting connected equipment from damage. SPD should be installed at various points in the electrical system, including the service entrance, distribution panels, and individual outlets. SPD come in different types, each designed for specific applications and voltage levels. Type 1 SPD are installed at the service entrance and provide the highest level of protection against lightning strikes and power grid surges. Type 2 SPD are installed at distribution panels and protect against surges from internal sources and less severe external events. Type 3 SPD are installed at individual outlets and protect sensitive electronics from local surges and voltage spikes. Proper installation and maintenance of SPD are crucial for their effectiveness. SPD should be installed by a qualified electrician and inspected regularly to ensure they are functioning correctly. Damaged or expired SPD should be replaced promptly to maintain protection against overvoltage events. In addition to SPD, there are other measures that can be taken to protect against overvoltage events. Firstly, proper grounding is essential. A well-grounded electrical system provides a low-impedance path for surge currents to flow to ground, reducing the voltage stress on connected equipment. Secondly, surge-suppressing power strips can also help protect electronics from damage. Use surge-suppressing power strips with sensitive electronics to provide an additional layer of protection against voltage spikes. Thirdly, unplug electronics during storms. Unplug sensitive electronics during lightning storms to prevent damage from surges that may bypass SPD. Fourthly, inspect and maintain wiring. Regularly inspect and maintain the home's wiring to identify and correct any issues that could lead to overvoltage events. Be especially mindful of the importance of small details, such as fully crimping a connection. These seemingly minor tasks can have significant consequences if overlooked.